Assalamualaikum and a very good day to all. My name is Nabihah Binti Khairul Anuar and I'm going to present my final year project titled Synthesis and Characterization of Activation Carbon using Bitter Melon Waste, a review. And my supervisor is Dr. Jeyashelly, and the content of this presentation I would like to present about introduction, literature review, conclusion and recommendation. In the introduction part, I would like to explain about research background, problem statement, significance of study and objective of this study. Bitter melon, or known as Perlis, is a quite well-known since the taste not very enjoyable, but is a perfect for health. There are a lot of uses for bitter melon, such as for medicinal. The uses of bitter melon are widely, but not for waste. The seed and the core always considered as waste since it is not editable part. Activated carbon, or AC, is a solid carbonaceous material with high physiochemical stability, high porosity, and high adsorptive capacity. AC production is used in water removal to remove organic and metal substances from the environment. There are various ways to prepare AC, which via chemical activation or via physical activation. From a study, there are numerous of ACs that are created from waste products such as avocado seed. In this review, bitter melon waste are used as precursor for the AC. Problem statement. The fruits and vegetable sector generate large amounts of waste. Seeds and core are non-editable parts of vegetables. To overcome this problem, the bitter melon waste from seeds and fibrous core have been recycled and reviewed as AC sources. Significance of studies. This study is represented on the production of ACs from raw material due to the excess production of agricultural wastes can be one of the factors of environmental pollution. Hence, the elimination approach has been reviewed by changing the product's waste into something that is valuable and can be used for another purpose to remove pollution in our environment. The objective of this study are the first one, to prepare AC from bitter melon waste with potassium hydroxide KOH activation. The next one is to characterize the prepared sample using scanning electron microscopy SEM, Fourier transform infrared spectroscopy FTIR, CH&SO analyzer, sodium thiosulfate for volumetric titration, iodine number, and percentile determination. We move on to literature review. Why I chose bitter melon? Bitter melon has been used as a traditional remedy for centuries and includes a variety of bioactive compounds. Bitter melon waste can be considered as lignocellulosic waste because of the way they are discarded, leading to the environmental problem. Major components of lignocellulosic waste are cellulose, hemicellulose, and lignin that contribute to AC formation. Based on the review that have been made from previous research, the composition of the precursor is essential to be chosen as AC. In this review, chemical activation is chosen. Advantages of chemical activation. Chemical activation is allowed activating agents to penetrate deeply into the carbon structure, resulting in the formation of tiny pores in the AC, expanding its surface. Chemical activation produces more carbon with a desired porosity, composed of micropores and mesopores, which make them more suitable for liquid phase adsorption. Chemical activation can have higher yield and lower temperature activation. The development of porosity is based on dehydration and degradation. Lastly, since the lower temperature and shorter treatment is qualified, the cost and energy consumption are reduced. Disadvantages of chemical activation. The activating agents can cost more because of additional and repeating washing stages to eradicate the spent activating agents from the final mixture at the end of the activation process. Furthermore, during the washing process, toxic water is produced, which can cause water pollution. Many activators can be chosen whether alkaline or acidic. Potassium hydroxide KOH. KOH is chosen in this review as chemical agent. KOH as a chemical activator is quite encouraging. KOH is acted as dehydrating agent where it inhibits the development of AC, which help it increase the yield of porous rubber. Next, AC with KOH activation had the best effectiveness in the adsorption of heavy metals. Besides, KOH can generate high-yield mesopores and micropores, carbon with high porosity and unique surface area. Lastly, KOH can be extracted easily by washing and leaching with water after activation. In addition, KOH activation is easy process with short activation time and lower activation temperature. The effect of activation condition. Previous studies have addressed the impregnation ratio and the carbonization temperature as gap where both affected the yield of AC. In this slide, I would like to talk about impregnation ratio. The impregnation ratio can produce a higher yield of AC. Impregnation ratio can be in 1:1, 1:2, and 1:4, which represent the weight of the char and the weight of the chemical agent. However, at certain point, the yield of acid decreased as the impregnation ratio of the chemical increased. Why? Because the potassium catalyzed decomposition of char occur, resulting in the decreased amount of acid produced. Carbonization temperature affected the pore volumes and the particular surface area. As the temperatures over 780 degrees Celsius, the potassium loss in the reaction is high, which is that temperature is the boiling point of potassium. As the temperature increased to 800 degrees Celsius and the impregnation ratio of KOH increased, the walls between the pore pools on the AC are further degraded. Thus, the surface area of AC is reduced, resulting in a reduction of AC's absorption power. The effects of parameters on the precursor are reviewed by characterizing into the SEM analysis, FTIR analysis, elemental analysis, and iodine number. SEM analysis. SEM image demonstrated the porous structure of the ACs. SEM revealed that surface of the ACs which had visible pores of different size that preserve the parent material cell wall structure. However, during impregnation ratio, the indication of the original cell wall structure is lost if the AC lack of a characteristic of wall structure. From the impregnation procedure, the lignin component which help in the precise shape of the biomass can be degraded, making porous structure non-characteristic. FTIR analysis. FTIR spectroscopy provided information on structure and content of active functional sample groups. The surface of a sample is composed of functional groups infused with oxygen such as hydroxyl, carbonyl, or carboxyl. Additionally, the surface of the sample consisted of additional heteroatoms such as oxygen, nitrogen, phosphorus, sulfur, and halogen rather than completely of carbon atoms. Elemental analysis. The elemental and composition of materials such as carbon, hydrogen, nitrogen, sulfur, and oxygen can be determined with the CH&SO analyzer. The presence of high concentration of carbon, oxygen, and hydrogen is due to the concept of the three main primary polymers which are cellulose, hemicellulose, and lignin. The carbon content increase in AC as the impregnation ratio and the carbonization temperature increase, which it can influence the elemental analysis. Iodine number. The most popular indicator for determining adsorption capacity is the iodine number. The iodine number is examined in this study using the sodium thiosulfate volumetric titration. As increased the impregnation ratio, the iodine adsorption of AC also increased. Additionally, as the iodine content increased, it indicated increasing the microporosity. However, the iodine number did not always correspond to the ability of the carbon to ingest various organisms. It used to approximate the surface area of the AC that increased in the size of the pore structure. As conclusion, the bitter melon waste can be converted to AC by justification from the scientific evidence that can be found from previous study which contain in this thesis. Many factors can affect AC production such as the composition of the biomass which are cellulose, hemicellulose, and lignin. Also, carbonization temperature, the impregnation ratio, and the chemical activator used. Next, the effects of parameter on the precursor are reviewed by characterizing into the SEM analysis, FTIR analysis, elemental analysis, and iodine number. For the recommendations, more study regarding bitter melon need to be done due to there are many traditional uses for bitter melons stated but lack of scientific evidence to prove the statement. Also, in this review, the bitter melon wastes are activated by KOH, so in the further any type of alkalis and acid activators such as zinc chloride can be used to compare which of the chemical activators can develop more pores. Lastly, there are many applications of AC such as air purification, deadsorption, drinking water purification, and others. Thus, AC of bitter melon waste should be made to as the application due to it is eco-friendly products and it can reduce the waste disposal.